Think about how strongly the Earth pulls you down. You are there every single day. If you were to jump right now, smack, you'd stick right back to the ground. Similarly, a paperclip falls and hits the floor instantly. But look at this. A tiny little magnet easily lifts that paperclip, defeating the gravitational pull of the entire 12,756 kilometer wide Earth, from its vast oceans to its massive mountains. How is this possible? Or, to put it into perspective, if we can never actually touch any object at the atomic level, what is that sensation at the tips of our fingers when we touch something? How is it that everything, from black holes to a refrigerator magnet, from the tides moving oceans to atomic bombs vaporizing cities in milliseconds, and even the electrical activity in our brains, can be explained by just four and only four forces? Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But can we explain everything? Because problems like dark matter, dark energy, and the matter-antimatter asymmetry cannot be fully explained with the physics we have in hand. Could it be that to solve these, we need to discover a fifth force? Today, let's lay these strange phenomena out on the table. First, let's look at the word force. It entered the English language via Old French force, which in turn comes from the Latin fortis, meaning strong. But in science, we first encounter its usage with Aristotle. Aristotle wrote that all objects want to be at rest and that a continuous force must be applied to keep them moving. Thanks to Galileo, we know today that Aristotle was wrong. Objects in motion do not tend to stop. On the contrary, they tend to preserve their current state of motion. As you might have memorized from high school physics, objects at rest tend to stay at rest, and objects in motion tend to stay in motion. The person who gave the first concrete mathematical definition of this fundamental physical law was Isaac Newton. Although Newton didn't originally write it in this exact form, his famous formula summarized as F equals mxa proposed that force is the product of mass and acceleration, the change in velocity. Intuitively, this makes sense. The more massive an object, the more force is needed to change its speed. Newton formalized this reality. What makes this formula powerful, a true Swiss Army knife of physics, is its generality. It explains planetary motion, friction, collisions, and even aerodynamics. However, don't just think of force as interaction between touching objects. In nature, apart from a few extreme cases, there is no such thing as touching at the atomic scale. When you press your hand against a table, the resistance you feel is actually electromagnetic repulsion. The atoms in your hand never actually touch the atoms of the table. There's always a gap. It is far more accurate to think of forces as interactions or communication. Think of it like calling a friend. You are distant particles, and the force is the exchange of information mediated by radio waves. In the standard model of particle physics, we have matter particles, fermions, on the left, and force carriers, bosons, on the right. Let's break them down. The strong nuclear force, gluons as the name implies, this is the strongest force in the universe. It holds quarks together to form protons and neutrons. It is 137 times stronger than electromagnetism and trillions upon trillions of times stronger than gravity. This is why a tiny magnet beats the Earth. The gluons, named after glue, bind quarks so tightly that if you try to pull them apart, the energy creates new quarks rather than separating them. The weak nuclear force, W and Z bosons, is the alchemist of forces. It is the only force capable of changing one type of particle into another, e.g., a neutron into a proton. Without it, stars wouldn't shine and elements wouldn't form. Its range is incredibly short because its carrier particles, $W caret plus dollar, $W caret dash dollar, $Z caret $0, are surprisingly heavy, heavier even than iron atoms. Electromagnetism, photons, light, electricity, magnetism, chemical bonds, friction, it's all electromagnetism. It has infinite range. The carrier particle is the photon. One crucial detail: interactions travel at the speed of light. If the sun disappeared right now, gravity and light would persist for another 8 minutes and 20 seconds. We wouldn't know the sun was gone until the last photons arrived. Gravity, the odd one out. It's the weakest force. According to Einstein's general relativity, It might not even be a force in the traditional sense, but rather the curvature of space-time geometry. As John Wheeler famously said, space-time tells matter how to move, matter tells space-time how to curve. We assume there's a carrier particle called the graviton, but we haven't found it yet. So why 4 forces? Why not 1 or 5? Actually, there are mysteries that the big 4 can't explain. Dark matter. Galaxies spin too fast. They should fly apart, but something invisible holds them together. Muon G, 2 anomaly. Muons wobble more than the Standard Model predicts. The X-17 boson, a potential new particle observed in beryllium decay anomalies. These suggest we might be on the verge of discovering a 5th force. Physicists dream of a grand unified theory. We've already unified electromagnetism and the weak force into the electroweak force. The goal is to unite them all into a theory of everything, a single, short equation that explains the entire universe. But gravity refuses to fit into the quantum puzzle. Perhaps the missing piece, or the 5th force, will be discovered by one of you watching this video. Until the next video, stay curious.